Okay, good morning, guys. Sorry I didn't have that link up a little bit sooner. I got prompted to change my Santa Fe password this morning as I started signing in, and it rejected all of my initial requests. They changed some of the parameters. But I'm excited today because we're going to start talking officially about continuity, which is kind of our first big step after we learn about limits. So we've got a reasonable idea of what limits are and how to take them. We've looked at a few different limit problems from different perspectives from the graphs versus using algebra tricks to find the limits. So I'd like to do a few things today, and they center around more work with limits and introducing this idea of a rigorous definition of continuity. So let's get started. QCam, oh, let me start talking to this. All right. So I've noticed more and more people starting to come to office hours. That's really good. I want to encourage you guys to come to office hours, even if you don't have a dire question, even if there isn't something that's like just driving you nuts, just so you can sit there and see how some problems are solved, see how I like to use notation. It's a really good idea to visit, at least one office hour a week. This is section 004. Today's a lecture. It is the 13th. Makes me think I put the wrong date there. Did I put the wrong date in that announcement? Oh, no, it's 002. I knew something was wrong. All right. So today, we're going to get a little more practice with limits. I'll section 2.3. Because I know we finished that a little bit rushed yesterday, and we always need more practice with these sort of things. And then we're going to talk about continuity. Oh, sorry, this is my password issues I was mentioning coming back. We'll deal with that later. I'm going to define and work with continuity, which is section 2.5. And you may notice that we're jumping over section 2.4. Section 2.4 is on the delta epsilon, or the rigorous or precise definition of a limit. It's not something we cover in this class. It's something we cover in the honors class. But if you're curious about exactly how we define a limit, precisely what we mean when we say closer and closer, take a look in the textbook at section 2.4. I want to begin our actual work today with any homework problems that you guys want to look at. So presumably you've been taking a look at homework 2. There are a bunch of limit problems in there, and a few people brought specific limit problems to my office hours. So in the chat, please let me know, what would you guys like to see for our first couple examples today? What limit problems from your homework would you like to work on together? Would you like to see a solution for? And while you're typing that, I will come over to WebAssign here. See, do I have a WebAssign thing open? I do. I found that this doesn't work unless I come back through here, because they're working on their API. All right, you're going to give me the bad gateway thing again? You won't work. Looks like we're good. Okay. So I don't see anything in the chat yet. And if you guys don't make suggestions, if there aren't particular problems you want to see, I'm going to grab a few at my discretion, but I think it would be most useful if you told me which ones you wanted to see. In the unlikely event that you haven't looked at the homework yet, I can scroll through here, and if you see something that intimidates, oh, let me turn off this key and solution. If you see something that is intimidating, let me know. Number 16, Robert would like to see 16. I'd be happy to do that. More of those password issues. think problems like number 14 can be a little bit tricky. Here you need to use a trick called multiplying by the conjugate. You would multiply top and bottom by the square root of 9 plus h plus 3. That's something we haven't done together yet. Number 15, the algebra involved here can be a little tricky. I would start by rewriting these each as fractions. This would be like 1 over 8 plus h minus 1 over 8 all over h, and then you would have a common denominator between those two fractions and try to simplify. Number 16 looks like a fun problem. Here, let's take a look at that. This is the one Robert wanted to see. So as I have it, we want to calculate the limit as t goes to 0 in the expression 9 over t minus 9 over t squared plus t. So let's come over here. Fabrice wants to see number 2. We'll go back to that. So this is a t squared. I want to just remind you the result of our conversation on Monday. If we wanted to, we could plug in t equals 0 here, right? That's essentially what we discovered from our conversation last time, is that the limit laws lead us to realize that if it's possible, we can calculate limits by plugging in. And that's what the first few problems in this homework set have you do. You split things up, you shove your limit into all the little spots where the limit is relevant. And the upshot is you get the same thing out of the limit that you would get from just plugging in the value, like just plugging in 0. Unless you can't plug in the limit. And in this case, we see if we try to plug in t equals 0, this first piece is clearly undefined, right? 9 over 0, 0 downstairs, that's bad news. The second piece would also be undefined. You'd have 9 over, well, this would be 0 as well, right? 0 squared plus 0. So we cannot calculate this by direct substitution. We cannot calculate this limit just following the limit laws and plugging things in. So here we're going to need to do some algebra. We're going to need to do some algebra to try and rewrite this function as some other very similar function that doesn't have a discontinuity or a problem at 0. Now, since I have a fraction here and a fraction here, my intuition is to go ahead and try and subtract those two fractions, to have a common denominator and subtract the two fractions, see what we get, see if we can't clean that up. The key to combining these two into a single fraction is going to be having a common denominator. So before I do that, before I'm able to make my common denominator, I need to see what the factors of these denominators are. The first guy is just 9 over t. The only factor in his denominator is t. The second guy, let me factor t squared plus t into t times t plus 1. And that will help me see what's necessary to get a common denominator. That's fine, Luke. So if you requested an extension, I should be able to see it, and I'll grant it as soon as class ends today. I go through and clear extensions about twice a day. If you grant them, if you request them, I automatically grant them. There's no point penalty or anything like that. So if I want to combine this and this into a single fraction, if I want to perform the subtraction here, I need these two things to have the same denominator. This fellow has a factor of t and a factor of t plus 1 in his denominator. This fellow just has a factor of t. So in order for these to have the same denominator, I need to give this piece right here a factor of t plus 1 downstairs. The only way to do that is to give the factor of t plus 1 to the top and the bottom, so I'm not changing the value of the function. This is sometimes called the multiply by 1 trick, where you multiply upstairs and downstairs by some factor in order to change the appearance of this expression without changing its value. So I would write that like this. Now here, when I clean this piece up, when I put these two fractions together, you'll see that the denominator will be the same as the denominator of the other guy, which will then allow me to subtract the two fractions. Upstairs, I'll have 9 times parentheses t plus 1, and it's important that you remember every time you see a fraction, fractions are grouping symbols. You need to think of the top and the bottom as being in parentheses. So I have 9 times t plus 1 upstairs there, and t times t plus 1 downstairs, minus 9 over t times t plus 1. These are our first few algebra steps. Now that these have the same denominator, I can subtract the two fractions the same way you always subtract fractions. You just subtract the top. So this is 9 times parentheses t plus 1 minus 9 all over t times t plus 1. I'm next going to distribute this 9. And notice I'm writing, and then t to 0. Notice I'm writing these equal signs. I'm always writing my limit. This is just good notation, and you should do the same. That numerator is going to be 9t plus 9 minus 9, and the denominator is still t times t plus 1. And these guys, of course, they go. They add up to 0. So I end up with lim t to 0, 9t over t times t plus 1. And the nice thing you'll see here is that after we do all this algebra, there's a common factor of t in the top and in the bottom, which can be canceled. Remember, you can only cancel common factors. But here it is true that t is a factor of the top and t is a factor of the bottom, so they can be canceled. And this is the step that makes the magic happen. Because once I get rid of this factor of t from the bottom, I can send t to 0. Right? It's the factor of t in the denominator that made it hard for me to send t to 0 in the first place, because I can't have a 0 downstairs. So let me continue this work over here. We have now lim t to 0, 9 over t plus 1. And this guy is now my very similar function without the hole at 0. So this guy is the one I can plug t equals 0 into to get my answer. And when I plug 0 in here, I just get 9 over 0 plus 1. Well, that's 9. So the limit here is 9. And all of these algebra steps are necessary. So take a careful look at these. Make sure you understand each step. And if there are any questions about any one of these moves or why anything came out the way it did, please take the time to ask. Okay, are there any questions on this problem? All right, I'm going to proceed in the order they were requested. So Fabrice asked for number 2. Let me come back to number 2, and then we will look at number 18. There may be time to look at number 45. There may not. I think 45 may have to do with some continuity things that we haven't discussed yet. Number 2 here is all about graphs. And I don't want to spoil the whole problem for you, because this is a really conceptually important problem. This is one that's important that you spend the time thinking about. So I'll do, how about 2 parts of number 2? Are there any strong feelings about which parts in number 2 we would like to see? I will do part A and part E, unless somebody has a really strong feeling about which parts you would like me to do. So in part A, we want to calculate the limit as x goes to 2 of bracket f of x plus g of x. Okay, so yeah, rather than A and E, I'll do A and F. Robert, how's that? So in part A, remember this is one of the first homework problems after we learn the limit laws. So the idea here is for you to apply the appropriate limit law. And one of our, I think the very first limit law is just that a limit of a sum of functions can be split up as the sum of the limits. So this is the same as the limit as x goes to 2 of f of x plus the limit as x goes to 2 of g of x. And the intent now is for you to look at the graph of f to figure out the limit of f, and to look at the graph of g to figure out the limit of g. If I look at the graph of f, I want to know what is the function value approaching as the x value gets closer and closer to 2. So notice that this 1 right here tells you that every hash mark along the x-axis is a single unit, which means x equals 2 is right here, if you can see my mouse pointer. So as my x values get closer and closer and closer and closer to 2 from the left, my y values are getting closer and closer to -1. And as my x values get closer and closer and closer to 2 from the right, my y values are getting closer and closer to -1. So from either side, the limit as x approaches 2 of f of x looks like -1, which means the overall limit, which is what we're dealing with here, as x goes to 2, does exist, because the one-sided limits from either side are the same. From the left, we're going towards -1, and from the right, we're going towards -1. So this first piece is -1. Now for the other guy, lim x to 2 g of x, we look at the other graph. Again, here's 1, here's 2. So as my x values get closer and closer to 2 along the graph of g, my y values are getting closer and closer to this value up here, which is 2. And we should look from the left and from the right separately to make sure the limit exists. But yeah, from the left, my y values get closer and closer to 2. And from the right, my y values get closer and closer to 2. So the overall limit for g does exist and is equal to 2. And now here we have the result, right? The limit as x goes to 2 of f of x plus g of x is equal to -1 plus 2. And on a good day, that's +1. So that's job done for part A. In part F, I'm going to jump down to part F now because I really do want you guys to work this problem on your own. The notation is a little bit odd, right? Rather than having a limit of some big mess, I have these two very separate things. I have f of -1 plus the limit as x approaches -1 of g of x. So first, let's address f of -1. We look on the graph of f of x. We come over here to x equals -1. They're not asking us for the limit as x approaches -1 of f of x. They're asking us for the actual function value. If they wanted the limit as x went to -1 of f of x, that would be the y value of this whole. That would be this guy. But they're asking for f of -1 itself, and that doesn't come from this whole. The actual function value is coming from this point. So when x is -1, f of x is 1, 2, 3, right? This guy is at height 3. So f of -1 is 3. So this first piece right here is 3. The second piece, they want the limit as x approaches -1 of g of x. So we need to look along the graph of g, and ask ourselves, as the x values get closer and closer to -1, which is this x value, what are my y values doing? So I'm a little dude on the graph of G, walking closer and closer to having x value -1 from the left. My y value is getting closer and closer to 2, right? As I sneak up on this guy, my y values are going to 2. And similarly, as I come in from the right, my y values are going to 2. So the limit as x goes to -1 of g of x is 2. So I get 3 plus 2, that's 5. So Luke asked a good question. Why did, in part F, on this first piece, f of -1, why did I take the value from the point up here rather than the value from this hole down here? And this is the distinction between the function value and the limit. If they'd asked for the limit as x approaches -1 of f of x, then that's about the pattern. That's about asking, what do these y values get closer and closer to as x goes towards -1? But because, oh, I see, yeah, okay, no worries. Just to clarify though, in case anybody else is curious, the actual function value comes from this. This is the actual point on the graph, right? The hole shows us that there is no point on the graph right here. It's an empty spot. The actual point on the graph is up here. So f of -1 itself is 3, even though the limit as x approaches -1 of f of x is 1. So yeah, it's because they asked for the function value. All right, now I do have to be a little bit sparing. Let me move to 18 and then we'll see how we're doing for time. If you do want to see more problem solved, remember you can come to office hours. That's really the best place to discuss problem solving. Okay, 18, we haven't addressed this either. So this is a perfect place to pick up. We still need to talk about the squeeze theorem. 45, is there anything we can do with this yet? Probably not, right? Find the limit if it exists. Now, limits at infinity we haven't talked about yet either. All right, so this is where we're going to jump off. We're going to return to our lecture. There's one theorem from section 2.3 that we haven't addressed yet, and it's called the squeeze theorem. So this is our lecture from section 2.3, continued. There's this theorem called the squeeze theorem. In France, they call this the policeman theorem, and I'll explain why. It says this: if, let's say, f of x is less than or equal to g of x is less than or equal to h of x, for all x near a, we've been using c, right? I'll use a. For all x near a, then the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x is less than or equal to the limit as x approaches a of h of x. In other words, limits obey inequalities. Right? If one function is smaller than another function, then the limit of that first function will be smaller than the limit of that second function. And you can stack these up, just like you can stack up the original inequality. In particular, if the outer functions f and h satisfy lim x to a of f of x equals lim x to a h of x, if the two outer functions both go to the same value, call it L, then the limit of the inner guy, g of x, has to equal L also. The reason this is called the policeman theorem in France, I like this a lot, it's very cute. They say if there's a policeman behind you, f of x, so you are g of x. If there's a policeman behind you and a policeman in front of you, and both of those policemen are going to the same place, the police station, then your ass is also going to the police station. All right? If the outer functions f and h satisfy, so Fabrice was asking what are these words here, I'm sorry for my handwriting. Yeah, in particular, if the outer functions f and h satisfy lim x to a of f of x equals lim x to a of h of x equals L, that is to say, if the function that's smaller than g and the function that's bigger than g are both going to the same number L, then g itself has to go to L. So again, the policeman analogy is, here's you, here's the cop behind you, here's the cop in front of you. If the cop behind you and the cop in front of you are both going to the police station, then your ass is also going to the police station. It's a cute analogy. The French are notoriously rebellious. Let me show you a picture in the textbook that will help to see why this might be useful. So they get into it. This is all stuff we talked about the other day. Here's the squeeze theorem, right? And they break these down into two separate theorems. The first theorem here just says that limits obey inequalities. If f is less than or equal to g, then the limit of f is less than or equal to the limit of g. And the squeeze theorem itself says if f is less than g is less than h, nearby a, and the limit of f is equal to the limit of h, both the same value, call it L, then the limit of g has to also be L. And here's the picture. So imagine this red function g is a function you're trying to take the limit of. I want to know what is the limit as x approaches a of g of x. But for whatever reason, that limit is really hard to take. We've seen in our homework that sometimes algebra-wise, these limits can be tricky, right? Multiply by the conjugate or do all this weird, algebra with fractions. Sometimes it can be tricky to figure out a limit using algebra, and we don't always have the graph. But if there's some other function h that is bigger than your guy, and some other function f that is smaller than your guy, and you know that both of those functions go to the same value as x goes to a, then you can deduce that your function g must also go to that same value. And we have an example down here. This squeeze theorem is important. It'll be important in this class as a source of examples and fun problems. It'll be especially important in Calc 2. So for example, let's try to calculate the limit as x goes to 0 in x squared times the sine of 1 over x. We've seen that the sine of 1 over x has a crazy graph near 0. Do you guys remember that? The really fast oscillations? So this is the note that you saw in the textbook there. Note, lim x to 0 sine of 1 over x does not exist. So it's useless to split this as lim x to 0 x squared times lim x to 0 sine 1 over x. Right? If we just jumped in using our limit laws, The limit law says, okay, well, you've got a product here. You can take the limit of each of those things separately. But it turns out that that doesn't work because this guy does not exist, right? This would look like 0 times dne, which who the fuck knows what that is? Right, it's certainly not clear. So if you want to attack a problem like this, you need a theorem. You need some tool that will come in and help you a little bit. You need the right, you need the right socket wrench. You need the right hammer for the job. And it turns out that the right hammer for this job is exactly the squeeze theorem. I'll give you a second to write, and then I'm going to tab over to Desmos. Why is your face on this book? Okay, everybody done writing?
Can you give me a second?
Sure.
Thank you. All right, I'm good.
All right, Desmos time. So Desmos is your friend. I invite you to use Desmos on the homework. Just don't cheat yourself into thinking you know graphs you don't know. So every time you use Desmos to look at a graph, here's the way to do this. Just go ahead and draw the graph by hand. My function f of x is x squared times the sine. Let me first look at the sine of 1 over x. Sine 1 over x. Everybody remembers this thing, right? Massively pathological. Really weird behavior near 0. It just starts bouncing back and forth infinitely fast. That's not something we can wrap our heads around. That's why this limit has a problem. But the function I want to take the limit of is not this, it's this. And if you look in here close to 0, it starts to look like this limit might actually exist. Even though we have this really fast oscillation, the function is kind of getting closer and closer to something as we go closer and closer to 0. It's bouncing back and forth like a motherfucker, but those bounces are getting smaller and smaller and smaller and smaller. And as we zoom in, it starts to look like maybe this thing is going to 0. Sorry, this is x times 1 over x. We actually need x squared times 1 over x. So we're zoomed in too far for him. Yeah, here's x squared times 1 over x. So we start to think that this limit might actually exist, right? Despite the rapid oscillations, despite the fact that this thing is wiggling back and forth really fast here, it looks like the function is indeed going to 0. But how would you show it? You can't pop open Desmos on a desert island. You can't look at this graph unless you have some sort of computer to show you the graph, because graphing this thing by hand is going to be very, very hard. But we have a theorem. So what I need to do is think of a function that might always be bigger than this guy, but still goes to 0 as x goes to 0. And think of another function that is always smaller than this guy and still goes to 0 as x goes to 0. So we need to think of, if this is our f of x, if this is our g of x, we called it g of x in the theorem. If this is our g of x, then we need to think of the bounding functions f and h from the theorem. So from the graph, we think this limit is 0. From the graph, this limit appears to be 0. Despite the quick oscillations from this guy, it looks like this guy might drag the whole thing to 0 as x goes to 0. So what we're going to do is use the squeeze theorem. We're going to try to squeeze our function which is, I'll call it g of x equals x squared times the sine of 1 over x. I want to squeeze this between two functions that are easier to work with. Here's a neat observation. Let me come back to just the sine of 1 over x. This function is indeed horribly behaved near 0. But do you notice anything about the y values? What's the biggest this function ever gets? What's the smallest this function ever gets?
1 either way.
Yeah, it never gets bigger than +1. It never gets smaller than -1. And this is true for any sine function, right? The sine function, no matter what you feed it as input, will always spit out some number between -1 and 1. That comes from the definition of the sine function. So observe that -1 is less than or equal to the sine of 1 over x is less than or equal to +1. And I didn't need the graph to know that. I want to be very clear about this. No matter what's inside the sine function, regardless of its insides, is always trapped between -1 and 1 because it's defined by the unit circle. It's only able to spit out y values from the unit circle. The only y values on the unit circle are between -1 and 1. Here's where we need to get a little bit clever. Remember what our goal is. Our goal is to use the squeeze theorem. And the squeeze theorem says if your function is trapped between two other bounding functions, then blah, 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 blah. My function is x squared times the sine of 1 over x. So I want to have this guy show up in the middle here. One of the facts of an inequality is that you're allowed to multiply through an inequality by any non-negative quantity, and it won't mess things up. So it is a consequence of this that -x squared is less than or equal to x squared times the sine of 1 over x is less than or equal to +x squared. I just multiply through every piece of this inequality by x squared. And that makes my function show up in the middle. Does everybody follow this?
Will this only work for sine functions, or can you do it with anything?
We can do it with anything. You have to have some starting point. So for sines and cosines, this is the obvious starting point. Sines and cosines are always bounded between -1 and 1. But there are lots of other bounded functions that we can work with in the same sort of way.
So why did you multiply it by x squared?
Because my goal, if we look at the squeeze theorem, my goal is to use the squeeze theorem. And the squeeze theorem begins with the statement, if your function g of x is trapped between f of x and h of x, then da 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 is true. So what I want to do in order to use that theorem is to make my function show up in the middle of that inequality. So we're able to start with this fact, which we know is true. And then I ask, how do I make my function show up in the middle? What can I do to this inequality to make x squared times the sine of 1 over x show up in the middle? And the answer is you can multiply through this inequality everywhere by x squared. If you multiply this by x squared, you get our function. So, okay, I'll just multiply through every piece of this inequality by x squared, and that gives me this, which has what I want. It has my function in the middle, trapped between two boundary functions. Does that make sense?
Yes, sir.
Okay,
Yes, sir.
cool. Yeah, this stuff is pretty heady, so don't stress about asking questions. It's all right, it's good. Now here's the magic. We take limits everywhere. Remember, limits obey inequalities. I want the limit as x goes to 0 of this function. That's my goal. So let me take the limit as x goes to 0 everywhere in this expression. The limit in the middle is the one I'm trying to figure out. I don't know what that is. But both of the limits on the outside are things that I know. The limit as x goes to 0 of negative x squared, we can figure this out. This is not a hard limit. You can either think about the graph. You know what the graph of negative x squared looks like. It's this parabola opening down, vertex at 0, 0. Or you can use the limit laws. The limit laws, one of them says that for any polynomial, you can calculate a limit by direct substitution. So if you plug 0 in here, you don't have any problems. Plugging 0 in here gives you 0, right? Negative 0 squared is 0. So you get 0 is less than or equal to the limit as x goes to 0 of x squared times the sine of 1 over x is less than or equal to, well, this limit is also 0. So the thing I want is on the one hand greater than or equal to 0, and on the other hand less than or equal to 0. There's only one possibility there. There's only one way for something to be trapped between 0 and 0. And that's if the thing is itself 0.
Couldn't you also have figured that out by multiplying the x squared and the sine 1 over x, well, replacing the x's and the x squared times sine over x with 0?
No, because the sine of 1 over x does not have a limit at 0. Remember, that's how we got started here.
Okay.
If we try to replace the x's in this expression by 0, you get, sure, 0 from this piece, but you get something that doesn't exist from this piece. And 0 times dne, we have no idea what that is. That could be dne. That could be 0. That could be plus infinity. It could be 5. There's no guidance from that because this piece is so badly behaved. So
Okay.
the point here is that the sine of 1 over x, his shitty behavior near 0 makes this guy hard to figure out. And that's why we need the theorem. Yeah, I can zoom in a little bit down here. So this is going to take some time to wrap your head around. We want to take the limit as x goes to 0 of this function, but it's hard. It's hard because the sine of 1 over x does not play nice near 0. He bounces back and forth infinitely many times on any open interval containing 0. But he is always bounded between -1 and 1, which means x squared times the sine of 1 over x is always bounded between -x squared and +x squared. Once you have this inequality, you can take limits everywhere, and you discover that your limit, whatever the hell this thing is, it's got to be smaller than 0, but it's also got to be bigger than 0. And we say, well, shit, that means it has to be 0. Yeah, let's look at the graph. Let me come back to our function here. Okay, here's x squared times the sine of 1 over x. And you zoom in on 0. I can rescale my vertical axes a little bit. Too much. And tell you what. Let's just reset that to the default zoom. All right, here's my function. Here's x squared times the sine of 1 over x. From this graph, it does look like this function is going to 0, but the little waves, the back and forth waves there that get so out of control, make it really, really hard for me to say what that limit is for sure. But look at this guy. The red function is always bigger than the blue function, always. And the red function is always smaller than the green function, always. The red function, which is my function, the function whose limit I want to calculate at 0, is always trapped between the red and the blue, or sorry, between the green and the blue. And since the green and the blue both go to 0 as x goes to 0, the red function, despite its wiggling back and forth, must also go to 0. That's the kind of high-level logic here for this. It will take some getting used to. All right? And in calculus, we're going to deal with a lot of heavy concepts like this. It's not going to be as straightforward as most algebra stuff. It's going to require some careful algebra work, but then also really stretching your brain to think about these weird concepts. Let me show you another example. Oh, it's not happy with that. Here's x times the sine of 1 over x. Again, the red function bouncing back and forth like a maniac. But as we zoom in, it looks like it might be going to 0. And we're able to find really what's going on here is I'm bounding above by the absolute value of x. And I'm bounding below by negative absolute value of x. The red function is always smaller than the blue, always bigger than the green. And since both the blue and the green go to 0 as x goes to 0, the red function must be going to 0 as well. So this idea of having a badly behaved function that's bounded between two nicely behaved functions. And if those nicely behaved functions both have the same limit, then the badly behaved function, no matter how evil it is, has to have that same limit. Here's my bad guy. Here's the cop behind him. Here's the cop in front of him. The cop behind him is going to the jail. The cop in front of him is going to the jail. So my dude also going to jail. This is how your solutions to squeeze theorem problems should look. You should tell your reader that you're going to use the squeeze theorem. Then you have to build up your inequality. Then you take limits everywhere in that inequality. And if the outer two limits are the same, only if the outer two limits are the same, but if they are, then you can conclude that the limit of the middle guy has to have that same value. If these both came out to 5, then I would say that the limit of the middle guy has to be 5. If these both came out to -2, then I could say that the limit of the middle guy had to be -2. And at the end, you should say why. What's the mathematical theorem that guarantees that this is true? The squeeze theorem. All right. We do have some other things to talk about, so I need to move on, but I invite you to rewatch this portion of the video. I invite you to look in the textbook. There is a reasonable discussion here. They work the same example we just did, and there's lots of wording here that you can go through and read, and they do precisely the same thing that we did. Okay. We need to start talking about continuity. From your pre-calculus classes, you're familiar with a few different ways a function can fail to be continuous. So we have an intuitive idea of what it means to say the function f of x is continuous. Usually it's something like we can draw the graph of f of x without lifting our pen. Right, that's kind of the intuitive definition of continuity. Mathematicians would say this as the graph of f of x is a single connected piece. All right, but I think the way it's often said when we're learning these things in algebra is that if the graph can be drawn without lifting up your pen, then that's a continuous function. But the definition of continuity shouldn't be dependent on something we as people do. It should be a feature that belongs to that function and exists independent of anybody trying to draw its graph. So mathematicians need to come up with a more rigorous definition of continuity, and it turns out that this is the right one. So here's the actual definition of continuity. It's something that happens one point at a time, meaning it happens at one x value at a time. The function f of x is continuous at x equals a, provided the limit as x approaches a of f of x is equal to f of a. And then we say f of x is continuous on an interval I, right? Maybe it could be an open interval, could be a closed interval, whatever. On the interval I, I'll just call the interval by that name. On interval I, provided it is continuous at every number a in the interval I. Finally, we say a function is just continuous full stop if it's continuous everywhere in its domain. At every number a in its domain. So this definition has some ups and some downs. Some ups, it's rigorous, right? It actually doesn't depend on us trying to draw a graph by hand. It has nothing to do, it's totally independent of anything any human ever did. Functions that are continuous just are continuous. They don't need us to do anything for them to be continuous. Another up is that it's built in terms of shit we know. We know what limits are. We know what function values are. We know what it means to say two things are equal. So we can ask, at any given number a, does the limit as x approaches a of f of x exist? And if it does exist, what is that limit? We know how to find f of a. You just plug the number a into the function f of x. This thing definitely makes sense. And we know how to compare two things and say, are they equivalent or not? You just calculate each of them and check and see if they're the same. Here's a downside. It happens one number at a time. You can't check using this definition whether a function is continuous like everywhere all at once. You can only check at one point at a time, which means you're going to get really tired trying to check at every real number whether a function is or is not continuous there. You would die long before succeeding. So again, this is a place where we're going to want to build up some theorems.
Professor?
Yeah.
What is interval I?
So I'm just using this as a stand-in for any interval, right? We know what an interval is, right? Like a to B interval.
Yeah.
So I here could be a closed interval, could be an open interval, could be a half closed, half open interval, could be the whole real line. It's just that, we like to say f of x is continuous on the interval 0 to 5. What does that mean? Well, f of x is continuous on the interval 0 to 5, provided f of x is continuous at every number a on the interval 0 to 5. Does that make sense?
Yep.
So you can just replace this by any interval, and that is what it means to say f of x is continuous on that interval. And then the last sentence down here is just saying if you want to call a function continuous, rather than saying is continuous at 2, you want to say f of x is a continuous function. That means it satisfies this definition at every number a in its domain. So you look at the domain of f of x, you ask, is this statement true for every number a in the domain of f of x? If it is, then you can say that f of x is a continuous function. Full stop, no qualifiers, right? Not like is continuous at x equals 5 or is continuous on the interval 2 to 7. You can just say it is continuous, period, as long as you know this statement is true for every number a in its domain. All right. So there's a handful of things I'd like to do here. I'd like to get you a little bit of practice using this definition, but before that, I want to just develop a theorem or two. Remember, we said that for any polynomial, just remind you, for any polynomial f of x, and any real number a, the limit as x approaches a of f of x is just equal to f of a. This is something we said last time, that you can take any polynomial or even any rational function as long as the bottom isn't 0 at a, and evaluate the limit just by plugging that number in. If you want to see a proof of this, I actually proved this in my honors version of your class. Look at the video from from Monday in the honors playlist on my YouTube channel if you want to see the proof of this theorem. This is something that we just said last time, that you can take limits of polynomials by plugging in. A consequence of this is I call it corollary or corollary. Corollary. All polynomials are continuous at every, or let's just say all polynomials are continuous everywhere. Right, because the domain of any polynomial is all real numbers. And this is the definition of continuity. So polynomial functions are continuous everywhere. And this is a fact that you learned back in college algebra when we asked, could this be the graph of a polynomial or not? One of the things you look for is whether there's any jumps or breaks in the graph. If there were, you said, oh, no, it can't be a polynomial. So yeah, polynomials are continuous everywhere. Another theorem. Rational functions. Those are ratios of polynomial, are continuous everywhere in their domain. So that is everywhere except where their bottom is 0. And then I've got one or two more little things. I'll give you a second to write. I know I've got a lot of words up on the screen right now. I also suspect we're getting pretty close to the end of class time. Yeah. All right. Just a second or two longer here to write. Sums, products, and composites of continuous functions I'll say it like this. If f of x and g of x are continuous at x equals a, then so are f of x plus g of x, which is the function we call f plus g of x. So if f and g are both continuous at a, then so is their sum, so is their difference, so is their product, and so is their quotient, as long as the denominator is non-zero at a. As long as g of a is non-zero, right? So if you have two functions that are continuous at some number, then when you add up those functions, the resulting function is continuous at that number. When you subtract those functions, the resulting function is continuous at that number. When you multiply those functions, the resulting function is continuous at that number. And when you divide those functions, the result is continuous at that number, as long as the bottom isn't zero at that number. And then the big one, their composite is also continuous at that number. This is a big deal. What this says is that if you take two continuous functions and glue them together in any way, the result is another continuous function. The proof of this theorem is actually quite hard. I'm not going to prove it for you. If you take a graduate real analysis class, this is one of the first things you will prove about continuous functions, is that if you take two continuous functions and mash them together in any imaginable way, the result is another continuous function. What this means is that if you take like sine of x and e to the x and some polynomial and multiply or divide them in any reasonable way, the result will be another continuous function because all of those that you started with were continuous. Okay. I'm going to pop up your homework again and take a look at one of the problems relating to continuity. Yes, don't sign me up, goddammit. All right, you guys are here. So definition of continuity. Let's state something a little bit easier. As a whole now. Talk about continuity from the left and from the right in just a minute. These are all kind of intuitive. Give number A. Yeah, again, a little bit too straightforward. Let's look at number 29. We're going to explain why this function is or is not discontinuous at the number A. And here, let me copy this down. e.g., this is homework 2, number 29. Explain why the piecewise defined function x squared minus 3x over x squared minus 9 for x not equal to 3 and 1 if x is equal to 3 is or is not continuous at x equals 3. All right, here we are. So I want to know whether this function, which is defined piecewise as the rational function x squared minus 3x over x squared plus minus 9 for every x not equal to 3, and 1 if x is equal to 3, is or is not continuous at 3. Really quick, this right here is a rational function. F of x is not rational, it's piecewise, but this piece is a rational function. So first I would say observe that for all x not equal to 3, f of x is equal to this rational function, x squared minus 3x over x squared minus 9. So as long as x squared minus 9, the bottom, is not equal to 0, this will be continuous because it is a rational function. And that was our last theorem from the previous page. Rational functions are continuous everywhere except where their bottom is 0. Now, x squared minus 9 is equal to 0. You can factor this. It's x minus 3 times x plus 3. So x squared minus 9 is equal to 0 if and only if x is one of plus or minus 3. So the only places where f may not be continuous are x equals 3 and x equals negative 3. Those are the only two places we even have to worry about. Now they asked us specifically to look at 3. So we're going to keep our attention focused there. But this observation is an important one. The only place where this function even has a chance of fucking up is at 3 and negative 3. Could fuck up at 3, could fuck up at negative 3, because those are the places where this thing is undefined, right? Those are the places where the bottom of this rational function is 0. Now they want us to look specifically at 3. To do that, I recommend trying to draw the graph, right? Or at least playing around a little bit with the graph. To get the graph of this apparatus, we need to work with this thing. X squared minus 3x over x squared minus 9. The top and bottom can both be factored. The top is x times x minus 3. And the bottom is x minus 3 times x plus 3. All right, these are our factoring skills saving the day. And they will do this again and again and again. You can cancel the x minus 3's as long as x is not equal to 3, but that's okay because this function is only defined to be this thing if x is not equal to 3. And what you get is x over x plus 3. Now, what I want to know is whether the limit as x approaches 3 of f of x is equal to f of 3. That's the definition of continuity. So I'd say f of x is equal to this for all x not equal to 3. We need to check, and this is the real point here, we need to check the definition of continuity at x equals 3, which is lim x to 3 of f of x equals f of 3. I need to check whether or not this is a true statement. since f of x is equal to x over x plus 3 for all x's besides 3, we can use this expression to calculate the limit. And then we're going to compare that to f of 3 itself. This could fuck up in one of three ways. The limit could fail to exist. Maybe the limit as x approaches 3 of f of x just straight up doesn't exist. Then the function can't be continuous at 3, because it's impossible for something that doesn't exist to be equal to some number. The second way this could fuck up, f of 3 might not exist. Maybe 3 isn't even in the domain of the function. That's not the case here, because I'll remind you, f of x is defined to be 1 at 3. So f of 3 definitely does exist here. But that's the second way this can fuck up. The final way this can fuck up is if both of those things exist, but they turn out to not be equal to each other. Maybe f of 3 is, well, we know f of 3 is 1. Maybe this limit comes out to like 5 or something, and 5 is not equal to 3. So we're trying to check this definition, and I think I said this last time, that this can fuck up in any one of those three ways. The limit can fail to exist, the function value can fail to exist, or they could both exist but not be equal to each other. Let's calculate, oh, okay, so we know that f of 3 is equal to 1. This is coming from the piecewise definition of f. Right, if you look back up here, f of x is defined to be this function for all x not equal to 3, and it's equal to 1 if x is equal to 3. So f of 3 is 1. All right, we know that. We can calculate. I'm going to move this up a little here. We can calculate the limit as x approaches 3 of f of x using the algebra shit that we did just a second ago. Right? F of x for all x not equal to 3 is equal to this thing, which means that the limit of f of x is equal to the limit as x approaches 3 of x over x plus 3. And that's not a hard limit to take, because we've already done all the algebra to cancel and clean this up. When you send x to 3, you get 3 over 3 plus 3, which is 3 over 6, which is 1/2. So is this function continuous at 3?
Yes.
I'm curious, why yes? Luke, really quick, sorry, Mackenzie, 1 second. Luke, no, sine of 1 over x is not continuous at 0. It's continuous everywhere else, but 1 over x is not continuous at 0, so sine of 1 over x is not continuous at 0. Remember, we required both f and g to be continuous in that theorem. We said if the two functions are both continuous, then however you mash them up, the result is continuous. 1 over x is not continuous, specifically not at 0. I'm sorry, Mackenzie, just responding to a question in chat. All right. What would we need in order to say that this function here, f of x, that we're playing with is continuous? We would need this statement to be true.
1/2 doesn't equal 1.
Perfect. Yeah, Robert's got it. F of 3, this thing is 1. The limit as x goes to 3 of f of x is 1/2. So, therefore, the limit as x approaches 3 of f of x, this was 1/2, is not equal to f of 3, which was 1. So f of x is not continuous at x equals 3. That's job done. These tend to be some harder problems. I'll be real straight up with you guys. The first few questions about continuity in your homework, you're not going to have any problem with. They're easy. But these guys, where you have to go in and investigate using the limit definition of continuity, they tend to be a bit tricky. If you fully understand limits, then they're not hard. If you fully understand limits and piecewise functions, which is two big ifs, right? If you fully understand limits and piecewise functions, then these are not hard. But if you have any gaps in your knowledge relating to piecewise functions from pre-calculus, or if you haven't fully internalized the work we've done so far this semester on limits, then you're going to find these to be very hard. Take the time to grind on these until you really understand them. Take the time, read the textbook, look at the examples, and make sure you really understand the shit, because it will be a big help as you move down, you move up the ladder in mathematics. Continuity is a big deal. It's a very big deal. All right. Let's take a quick look at the graph of this function. Let's see how I'm doing for time. Oh, no, we're out of time. All right. So this is where I have to end the lecture for today. We did resolve this problem. I invite you guys to try and graph this function f of x. That would be a great little project for anybody who's wanting to really understand this or is having a slightly hard time understanding this. See if you can graph that function. Right. Graphing this is not terribly hard. The algebra work is all right here. So for all x not equal to 3, your function is this guy. You should know how to graph this function, BT dubs, right? This is a simple rational function. We make people graph this sort of thing in college algebra. We make you graph much harder things in pre-calculus. Unfortunately, the homework only ever makes you pick the graph from a set of 4 graphs in WebAssign. So maybe not everybody has tried. So take the time to graph this function by hand. If you don't know how to do that shit, you got to learn it. You got to learn it fast. Use this graph and this piecewise definition to try and draw a graph of f of x. What you'll find is that there's a little hole and then a filled in point above that hole. The hole is going to be at 3, 1/2. And the filled in point is going to be at 3, 1. And everywhere else, it's going to look like this guy. All right, I have to get running. I do have an office hour today. Remember, you can join the office hour through the links in Canvas. I highly recommend you do that if you haven't yet, just so you can get a feel for how office hours go. And we can talk through any problems that you want to talk through. Otherwise, you can get a hold of me through Canvas messages or email. And that is it. I will see you guys on Friday when we will be talking about limits at infinity. I'll do maybe one more continuity problem on Friday, but then we're going to spend the rest of the class talking about how to take limits at infinity. You guys have a lovely rest of your day, and I'll see you next time.